So yeah, something a little different now. We're going to talk about equine gene doping and its detection and what the IFHA has been doing over the past few years to make sure that it doesn't become a big problem. So it was as long ago as in the 1960s that scientists first thought that they might be able to treat genetic diseases using the insertion of DNA to replace something that was faulty. So they knew that there were genes in cells and that genes produce proteins, and that sometimes these genes have mistakes in them, so the proteins don't work properly. And this can cause very serious disease, if not fatal disorders. And so they thought maybe we'd be able to insert a correct copy of the gene, put it into the cell, and then the cell will produce the protein, and then the person will get better. So this became a reality in 1990 when a 4-year-old girl who had an immune disorder, so it meant that if she was subjected to like a normal minor cough or cold, she could die at any time, was given the very first genetic therapy, and it actually worked, and she's still alive today. So this then launched many clinical trials and research into genetic therapy. A landmark study that was published in 2001 was aimed at developing a treatment for muscular dystrophies. So this is where the muscles are very weak. So they inserted a gene called IGF-1, which stands for insulin-like growth factor, so a growth factor to make the muscles big, into some mice. And you can see the normal mouse is the wild type, and then the other mouse is the one which has the gene inside it, an extra copy of the gene inside it. And these treated mice had between 25 and up to 70% more muscle mass, and this translated into increased strength. So they actually were stronger, and they were also protected from the normal age-related loss of strength as well. So the day after this was publicly released to much fanfare, one of the professors on the paper opened up his emails and found 5 emails from American football coaches and 1 email from a horse trainer asking when his therapy would be available for public use. So I think that might have been when the idea of gene doping was born. I'm going to talk to you about one more genetic therapy study that it's my favourite one, so that's why I like to talk about it. In this study, they inserted a gene that helps make glucose available for metabolism, for energy. So what they found was the mice that had been treated with this gene were 7 times more active in their cages than their normal counterparts. My favourite bit, they ate 50% more, but were 50% lighter in body weight than their normal counterparts. And the graph that you can see on the screen here shows that they put all the mice on a little treadmill, and the normal mice could run for about 200 metres, whereas these treated mice, the treated mice here could run, some of them could run 4 kilometres and even as far as nearly 6 kilometres. So I'm sure some of you have heard of Parkrun. It's a 5K fun run. It's held all over the world on a Saturday morning. I have done it. Can you imagine a little mouse doing Parkrun next to you? They take about 5 hours to do it, so slightly slower than me. So those are both sort of the traditional idea of gene therapy and what most people think about when they think about gene therapy. But since then, there's been a next generation type of gene therapy called gene editing. And this, as the name suggests, is a much more subtle edit of the genetic material. So what it involves is insertion of the editing treatment, and the gene editing material looks for a very specific sequence, a piece of DNA, and it will actually cut that sequence at the target there. And that's why you'll see in the popular media that it's often referred to as molecular scissors. And so what then the DNA does is try to repair itself, and the gene editing sort of persuades the DNA to fix itself in a particular way. So you can actually change the original sequence, hence the edit. The most popular or commonly used type of gene editing is called CRISPR. Some of you may have heard of it. And CRISPR was first published in 2012, and the two women that led that research were awarded the Nobel Prize in Chemistry in 2020 for this particular work. And there are literally thousands of studies looking at gene editing in animals and plants, and humans as well, to develop these therapies. In fact, if you're wondering whether any of this actually translates into real life, there are a couple of gene-edited foods that are approved for consumption, and the first gene-edited food that was approved for consumption by the public was a gene-edited tomato, which is available here in Japan, and it's been edited to be more nutritious than your standard tomato. So what does this all have to do with racing? So the history of horse racing, we all know the sort of basic history of horse racing, but there are records that indicate that horse races were held in ancient Greece and ancient Rome. And I don't know about you, I have a suspicious mind, and I think that they were probably trying to cheat back then in ancient Rome as well. And the earliest mentions that I could find of actual doping in horse racing was in the 1600s in the UK. And so, again, this idea that you can that where there is competition, there will always be some sort of cheating. What a lot of people don't realise is that a lot of the time, doping agents are actually items or chemicals that have been developed for therapeutic use. So these are all been designed to help treat a problem or condition, but if they are used out of context, then it can constitute doping. So I'm going to sort of two types of gene doping here because we treat them slightly differently. So one is those first two studies with the mice where you insert the genetic material to produce a protein. And then the other is that gene editing, which is in horse racing terms, this is a much more serious type of gene doping. So if you remember, that IGF-1 paper was published in 2001. And the World Anti-Doping Agency added gene doping to their list of prohibited practices in 2003, so it got a lot of attention. And it was first discussed in thoroughbred racing at a conference of the racing analysts and veterinarians in 2004. Now, it might look like then racing didn't do so much in between that and forming a committee to deal with it, but there was actually quite a lot going on in the background with introductions of new rules and research into what it actually was. And it was then decided to form the Gene Doping Control Subcommittee, which is a subcommittee of the Advisory Council at the IFHA in 2016. And that was chaired by Dr. Kenichi Kasano until the end of 2019 when I took over as chair. Just to tell you what we do, our main aim is really to just gain this understanding of what gene doping is, and then to be able to translate that into knowledge for racing authorities so that we can ensure that it doesn't become a big problem in racing. We have some objectives. Revising the international agreement, which for those of you who aren't so familiar with it, it's almost like a set of model rules that helps to guide authorities on things they might want to regulate. So a major revision was done in 2019, but we're continually revising this as well, so we're going to submit some more changes soon. I've mentioned on the slide, one of our objectives is to clearly define gene doping and various terms around that. If you go to the international agreement, you'll find that there's actually not a clear definition of gene doping. But if you actually look for definitions of other doping agents, you'll find they're not there as well. And that's because if you are too specific on what you are going to prohibit, that makes it quite simple for people to just sort of get around that on a technicality. So we tend to try and be a little broader on how we prohibit stuff. We also regularly review what current therapies are available for horses, and see whether we need to think about dealing with those under the international agreement. So, for example, something that we've looked at recently is in 2020, with the global pandemic, 2021, a number of vaccines were developed by various companies which actually had world-first technology because they contained genetic material. So they're a type of genetic therapy under certain classifications. So what we wanted to do is make sure that these genuine therapies that have a legitimate use and don't have any issues with enhancing performance are not prohibited. So one of the things we have done is ensure there's an exemption for their use in the international agreement. Another objective was to make clear which genetic and cellular practices have no place in horse racing and breeding, and this is where we have placed gene editing. And there are a number of reasons why we have prohibited all forms of gene editing, but the main one is that gene editing works very, very well in a cell, but if you try and put it into all of the cells in a body, so that's trillions of cells, it can't really get into them and it doesn't work very well. So what everyone does then is use it in embryos, and particularly a very early embryo where there is only one cell and only one set of DNA to edit. So because of this will modify the heritable genome, which is absolutely not permitted in thoroughbred breeding. So it's very clear that we needed to prohibit this practice. Again, if you're wondering whether this is actually really happening, there are 3 published papers that I know of that have looked at or documented gene editing in horses. 2 were to correct single gene disorders that we can simply test for with genetic tests in quarter horses. But one was to remove or knock out the function of the myostatin gene in polo ponies, and cloned polo ponies at that. And so some of you may know the myostatin gene is a regulator of muscle mass, and it's also the gene that has natural mutations in it that are the basis for the speed gene test as well. In 2017, there was a group they're a group that regularly produces cloned polo ponies, announced that they would soon be having gene-edited polo ponies hit the ground in 2019. However, this didn't eventuate, because I'm sure if they had all these lovely, healthy foals running around, they would have made sure we all knew about them. And what that tells me is that it didn't work very well, and the reality is it's still a very new technology. However, they have recently, I think only this year, again said that soon they will have gene-edited foals being born. So they're certainly still working on it, and it's not put them off. Another objective is to provide guidance for the proper control of these gene therapies. So at the moment, we have prohibited the use of gene therapies under most conditions. And again, this is because there are no gene therapies licensed for use in horses. There are serious risks involved with any new therapy. So I told you about the young lady, or middle-aged lady now, who first received a successful gene therapy in 1990. In 1993, a young man called Jesse was unfortunately the very first person to die from a genetic therapy. So, there have been many cases throughout history, and those newspaper clippings come from 2022. So there are still people that are dying from these new therapies. So they are risky. However, again, we don't want to stop people from using something that is a genuine therapy that will help horses. So there are provisions made to use them under certain circumstances in the international agreement. And then finally, to recommend systems and policies for the detection of gene doping in horse racing. So the first paper on equine gene doping detection was published in 2017. And at my last count, there were 29 peer-reviewed papers published. I may have missed 1 or 2. There's usually one come out every few months. And the wonderful thing about our committee is that whenever there is some research published or someone has published it themselves, they will send it around to everyone so we can continue to monitor and watch these developments come. I have to thank the Japan Racing Association and the Laboratory of Racing Chemistry have done a huge amount of work in this space and recognise their contribution to this work. So most of these initial papers are focused on detecting that gene transfer, so that insertion of the genes. And I'm going to talk about how we do that on the next slide. And then just as a little aside, we've also been working on an information portal so that if you, as a member of a racing authority, would like to get more information or can't remember anything, you'll be able to go to the IFHA website, look at the gene doping control subcommittee page, and we will have information there for you. So just some basic stuff, how it works and what you might be able to do to help regulate it. So how do we detect it? So when you insert a gene for gene therapy, you actually want that piece of genetic material that you're inserting to be as small as possible. So you want it to be this size. And that is because the bigger the piece of DNA you put into the cell, the less likely it is to work. Luckily for us, in our gene doping detection, natural normal DNA, genes, are not like continuous and small. So a gene is just a piece of DNA that will then be turned into a protein. And if you look at the very top row here, we have these coloured blocks. And those indicate the parts of the gene which are turned into the protein. But you'll see in between them, they have areas of DNA that are not turned into the protein, so they're not really useful for that. So what they'll do is chop those pieces out and just insert that small piece of DNA where all of it is turned into the protein. What that then does is create some unique sequences where the pieces of non-protein making DNA have been cut out, so here and here and here. And again, the COVID pandemics has been quite helpful to us explaining PCR, because many people now know, having had PCR-based tests to detect COVID, that a PCR is just a very, very commonly used laboratory technique. The instruments themselves can be quite cheap. And what it does is it detects a very specific piece of DNA, and it's very specific, and depending on your machine, it can be very, very sensitive as well. So it's a very simple test really to use. So we're now more focusing on the detection of gene editing. And we're doing this by comparing the DNA sequence of a foal to its parents. And this is because if gene editing is going to work, it will be done on the embryo. So by the time the foal is born, any trace of that gene editing material will be gone. You won't be able to find it. So instead, we're looking for the product of that editing. And the change on both copies of the DNA, so a foal inherits half of its DNA from its dam and half from its sire. And if it has a new change on both of those pieces of DNA, that's indicative of something that's artificial. That shouldn't happen naturally. So this is a very simple concept, but the reality is it is expensive. We use a technique called whole genome sequencing. The actual cost of whole genome sequencing is coming down, but it is still in the ballpark of, say, $600 US per horse. It's also technically very difficult, and it uses a huge amount of computer server space and processing time. And that's actually the real difficulty, is you really need these specialist skills to be able to analyse the data. And there's a lot of data. So a full sequence from one horse can be a terabyte. So if you think about a disc with a terabyte on it, and then how many horses you have to do, that's actually like quite a large logistic problem. The final sort of obstacle to this is we need to research what normal horse DNA variation looks like. We sort of assume that we inherit an exact half our DNA from each parent, and it's an exact copy of what our parents have. But the reality is, if you have particularly sperm cells where they're making millions and millions of sperm cells, there are going to be little mistakes made in the copying. And that's how genetic diseases arise, and it's how genetic variation occurs. And there's actually a small number of these variants that occur in every generation. And so, for example, this foal has a new variant that we didn't know about before, and we know this because she's pure white, so she's a genuine white foal. Her dam is chestnut, as you can see in the photo, and her sire is bay. So there are many families of these white horses, but they don't happen very often because it's obviously very rare. And there's one gene where it appears that that a variant in that creates the white foal that you see. And there are a couple of very famous white families here in Japan as well. So what we really need to do is get an understanding of what the normal variation looks like, so that when we are looking at a sequence of a foal, we can say, no, this definitely looks abnormal. This is not correct. And then we can go back and prosecute based on that. So what we want to do is really prevent this happening. So these are some fake news headlines that I have made, but the idea that a colt might be born that is edited and then born, and then produces foals that have inherited that edit, that then race as well, that's, I guess, possibly the worst thing that could happen for thoroughbred breeding. So we really want to make sure that doesn't happen. The good news is, as I said, I really don't think it's a very good technology yet, so we do have a little time on our side. And then finally, I actually first wrote this slide, I think in 2015, thinking about what a good, and it could really be a good anti-doping program look like. And we've made some great progress here. So the first step is to prohibit. You can't really do anything about something unless you take a stand on whether it's right or wrong. Education. And so I have to thank you all for allowing me to come and educate and distribute the knowledge that we've been trying to build up over the past few years. And one thing we do want to highlight is that all doping, I mean gene doping as well, but all doping can confer serious health risks, so it can be quite dangerous to the animal being doped. Detection, we're halfway there. The gene transfer detection tests are working. There are many labs that are either developing them or using them already. So that's really reassuring. I should point out we also have the advantage over our human counterparts in that we can actually gene dope a horse and then test whether our tests work, and they do work. And then I've written intelligence there. So the most famous doping case of all, Lance Armstrong, he never tested positive for anything. So there are other factors that we need to consider to be able to prosecute and find out about these doping cases. And then I've mentioned the research to establish what is normal. So thank you very much for allowing me to meet my commitments to the Gene Doping Committee.